Welcome back. After having studied the basic radiation heat transfer, we're ready for some advanced topic, radiation heat transfer in participating medium. First, let's review the basic heat transfer mode: conduction, convection, and radiation. These three heat transfer modes distinguish from each other by its own heat carrier. For conduction, the heat carrier is molecules. For convection, it is the moving fluid. And for radiation, the heat carrier is electromagnetic waves. Therefore, for each heat transfer mode, it has its own mathematical equation to calculate the heat rate. Second, compared to conduction and convection, radiation heat transfer has its own uniqueness, which is 1. Radiation heat transfer can take place without the presence of a material medium. 2. Any matter, material, or medium, as long as temperature is above absolute 0 Kelvin, it always emits radiation energy. Therefore, it's safe to say radiation heat transfer always exists. And if a vacuum is present, like in outer space, radiation is the only mechanism for heat transfer to occur. B. Since radiation is very unique, how do we characterize the radiation heat transfer process? First, we introduce radiation heat flux to represent emitted power, radiosity, and incident radiation. Second, we introduce radiation properties to measure the medium ability to emit, absorb, reflect, or transmit the radiation heat. Third, we introduce net radiation heat rate to account the radiation exchange for a single surface or between any two surfaces. Finally, if the system is closed, the radiation energy is conserved. Once we have all the physical variables to characterize the uniqueness of radiation heat transfer, we wonder under what conditions we have been studying radiation heat transfer. There are 4 of them. 1, radiation system is a closed system. 2, system surfaces are gray, diffusive, and isothermal. 3, the system surface are opaque, which is that there is no radiation transmitted. 4, The medium separating the system surface is non-participating, like the air at a room temperature and pressure. It doesn't impact the radiation heat transfer. Therefore, all the radiation interaction is limited between surfaces. This phenomena is called surface radiation or surface radiation process. This has been our focus. D. We would wonder what the radiation heat transfer looks like if the medium is participating. First, the medium is defined as participating because they have the ability to alter the radiation heat transfer through absorption, emission, and scattering. Some participating medium example include gases at a moderate over high temperature, and it contains asymmetric molecules, H2O or CO2, or it contains the small particles like dust and soot. Another example of participating medium is the semi-transparent solid or liquid like the glass. Second, how the participating medium alter the radiation heat transfer. There are two mechanisms. A. The radiation energy can be augmented when the radiation travels through the participating medium by the local emission, which pushes the photons into the radiation ray, and by in scattering, which is the photons is scattered into the radiation direction. The second mechanism is the radiation energy when it travels through the participating medium can be reduced by the local absorption because less radiation energy will be leaving the medium, and by the outer scattering, which is the photons is or are scattered away from the radiation direction. For example, in this furnace, the radiation heat flow from furnace bottom travel through the fire at 2000 Kelvin, reaching the top plate surface. Obviously, the fire is the participating medium because it is increased the radiation heat flow. E. Once we define the participating medium, we want to know how mathematically describe the participating medium impact on the radiation heat transfer process. First, radiation is often viewed as electromagnetic waves and transport of massless energy particles called photons. Therefore, the radiation heat flux is visualized to travel along the straight line, and the radiation heat flux magnitude will depend upon the travel direction and wavelengths lambda. Second, we introduce a volumetric angle called solid angle to define the radiation heat travel direction. This travel direction in a spherical coordinate system is determined by the plane angles theta and phi, as well as a unit vector s hat. Third, the solid angle, its magnitude is related to plane angle theta and phi in equation 2.1. It has the unit of steradian, SR. Its direction is related to the unit vector s hat through equation 2.2. Once we define the solid angle, we're ready to define radiation intensity I, which is radiation heat rate per unit wavelengths per unit solid angle and per unit surface projected surface area. The usefulness for radiation intensity is that we can specify radiation heat flux like the emitted power E or incident radiation G. Now, we're ready to do a simple derivation on radiation transfer equation, RTE. First, we have a participating medium with thickness L. The radiation is traveling through the participating medium. 2. We define a differential control volume taken from the participating medium with differential thickness ds and cross-section area dA. Third, the radiation intensity I is traveling along the direction S hat. Now, a beam of a radiation ray with intensity I sub lambda s is incident on the differential medium and lives with intensity of I sub lambda s plus ds. The medium is participating by altering the radiation heat transfer through the following contributions. 4.1 local absorption, 4.2 scattering out. These two contributions will reduce the radiation intensity. Therefore, negative sign is given. 4.3 emission in and scattering in. These two contributions will augment the radiation intensity, therefore positive sign is given. Where alpha is the absorptivity, rho is the reflectivity, epsilon is the emissivity, ds is the differential thickness, I is the radiation intensity, and the phase function phi describes the probability that a radiation ray from one direction can be scattered to another direction. D omega is the solid angle. Now we're ready to apply energy balance to our differential control volume of the medium with the radiation intensity traveling in the direction S hat. It states that the change in radiation intensity is due to the participant medium emission, absorption, scattering out, and scattering in. By applying Taylor expansion to the left-hand side and substitute for each term, a term from the previous definition 4.1, 4.2, 4.3, and 4.4, we obtained the radiation transfer equation RTE represented here. H. Then we see what's the significance or usefulness for the radiation transfer equation. The first usefulness is that we can evaluate the radiation properties. For example, once we obtained the radiation intensity for the emitted radiation from solving the radiation transport equation. We can evaluate the spectral directional emissivity. The subscript lambda and theta represent they depend upon wavelength and direction. If we integrate the radiation intensity over all direction, we will get spectral hemispherical emissivity. If we integrate radiation over all wavelength, we will get total but directional emissivity. If we integrate radiation intensity over all direction and all wavelength, we will get total and hemispherical emissivity. That's the emissivity we've been using in the basic radiation heat transfer. And finally, with radiation emissivity, we can get the emitted power, the heat flux as well. The second usefulness or significance of radiation transport equation is that after solving the equation, we will get the radiation intensity. Then through the integration, we will get radiation heat flux. So once we get a radiation heat flux, if our system, like the fire, we define a differential element, not only does it involve conduction across the system boundary, but also convection and radiation in and out of the system. We still have the same energy conservation, but for this combined conduction, convection, and radiation cross the system boundary in and out. For example, in the Cartesian coordinates and two-dimensional, the energy conservation equation is conduction, convection, and radiation cross the boundary with energy generated to contribute the change of enthalpy within the system. And in this equation, this is called radiation heat flux divergence. In 2D geometry and Cartesian coordinate, the radiation heat flux divergence is defined in equation 2.1. So this is the second usefulness or significance for the radiation transport equation. And also, for the first time, we showed you the complete energy governing equation. However, these two equations are extremely difficult to solve. For example, the temperature often are unknown, so we have to couple these two equations to solve to get temperature, and these two equations become differential integral equation. So this is going to be the topics you will study further in the advanced radiation. At this point, we covered advanced radiation heat transfer in participating medium. First, we introduced participating medium and defined radiation intensity. Then we did a simple derivation on radiation transport equation and discussed the usefulness and significance about the radiation transport equation. Finally, we showed you the complete energy equation with all conduction, convection, and radiation across the system boundary. However, what we did not cover is the methods to solve the radiation transport equation and the method to find a view factor. We have been using the algebraic method to determine the view factor through the tables and the view factor rules. But since the system geometry could be very difficult, so it's challenging to find the view factor value. Finally, we did not cover the solar radiation. At this point, we complete advanced radiation with the summary and outcomes of concept, variables, scales, and equations. We end advanced radiation. Bye.